Right, so in this class we are going to discuss about effect of nuclear spin on rotational Raman spectroscopy or spectrum of a diatomic molecule. Okay, listen, when molecule undergo rotation, see, suppose I have a diatomic molecule, this is nucleus of one atom, this is the bond, and this is nucleus of another atom. Don't worry about the electronic arrangement. I am just showing you the nuclei and the bond. When the molecule undergoes rotation, what happens is that this nucleus comes here and this nucleus goes here, correct? They continuously exchange the nuclei during rotation, right? So listen, the nucleus, right, present in the molecule may have spin. Okay, yes, most nuclei have spin. If, depending upon the spin possessed by the nuclei, we classify the nuclei into bosons or fermions. Okay, if we denote the nuclear spin by a quantum number called nuclear spin quantum number I. Right. So when molecule undergo rotation, what happens is that nuclei are exchanging their position, and nuclei may have some values for spin, nuclear spin quantum number. If nuclear spin quantum number is 0 or 2, 1, 2, 3, etc., integer values, we call those nuclei, okay, those nucleus or those nuclei are called as bosons. Okay, if any nucleus has I value 0 or 1 or 2 or 3, etc., integer values, then that nucleus is called as a boson. If nuclei possess spin quantum number value half or 3 by 2 or 5 by 2, right, or 7 by 2, etc., then those nuclei are called as fermions. Okay, boson is a singular, bosons means plural word. Okay, I am writing in plural form. Now, in the case of homodiatomic molecule, observe carefully. In the case of homodiatomic molecule, what happens is that both the nuclei are same, right? In the case of homodiatomic molecule, both the nuclei are same. So when molecule undergo rotation, what happens is that the nuclei exchange their position. Okay, and since they are homo, both the nuclei are identical nuclei. Both the nuclei are identical. So both are either fermions or both are bosons. When two identical fermions exchange their position during rotation, then total wave function must be antisymmetric. If two identical bosons exchange their position, right, during rotation, then the total wave function must be symmetric. Okay, listen, rotational motion exchange the nuclei, right? Since in homodiatomic molecule both the nuclei are identical, so during rotation of the molecule, okay, either fermions, identical fermions exchange their position, or maybe identical bosons may exchange their position, right? And you know very well, if the identical fermions exchange the position, then the total wave function should be antisymmetric. If identical bosons exchange their position, then the total wave function must be symmetric. This is what we call as Pauli principle, right? And listen carefully, this exchange of identical bosons or identical fermions affects the rotational Raman spectrum of the diatomic molecule, right? See, nuclear spin, presence of nuclear spin, okay, affects the rotational Raman spectrum of diatomic molecule, very specifically homodiatomic molecule. Okay, nuclear spin affects the rotational Raman spectrum of homodiatomic molecules. Okay, how it will affect? Usually it affects in two ways. First one is, there may be alternation in intensity occur, alternation in intensity of the line, or there may be missing of rotational lines may also occur. Okay, so nuclear spin, right, affects the rotational Raman spectrum. Either it alternates the intensities of the adjacent lines, or it will, the effect of nuclear spin may cause missing of rotational lines. See, in the rotational Raman spectrum, I have told you, there are many rotational levels exist in the ground electronic state. See, these are all rotational states available in the ground vibrational state of the ground electronic state. Observe carefully. These are all rotational states, J0, J1, J2, J3, J4, like that we have so many rotational states. These are rotational states associated with the ground vibrational state of the ground electronic state. Okay, and there may be some virtual state. Virtual state, usually we put dot symbols. Okay, virtual state. What happens when molecule absorbs? See, you know very well, in rotational levels, populations are almost right high, right, even at higher rotational levels. So, molecules present J equal to 0 state, J equal to 1 level, J equal to 2 level, right? Almost all rotational levels are highly populated. When molecule present in the J equal to 0 level, when the molecule absorbs a photon, it goes to the virtual state. That's the first step. Then it returns back and stays at the J equal to 2 level. Right? This transition, we call this transition, okay, simply as 0 to 2 transition. Okay, actually, listen, when molecule goes here to here and return back to this place, listen, this much energy, right, is taken by the molecule. Okay, so I can say that this is 0 to 2 transition, right? 0 to 2 transition is shown like this, and 0 to 2 transition will produce a line. See, this is the Rayleigh line, and it will produce a line. 0 to 2 transition produces a line in the spectrum. Then similarly, molecule may move from J equal to 1 level. Let me write here. Molecule absorb the radiation and can go from J equal to 1 level to the virtual state and return back to J equal to 3 level. Right? And this transition is what we call as 1 to 3 transition. 1 to 3 transition appears, right? Appears as Stokes lines because they are starting from the lower level. We have corresponding anti-Stokes lines also. Sometimes molecule may move from higher J equal to 2 and goes to the virtual state, and when it returns back, it goes down to the lower level. And this transition, okay, it is called anti-Stokes line, and this is also 0 to 2 transition. 0 to, the difference is, see, this is 0, this is 2, so this is also 0 to transition, but anti-Stokes. So this appears in the other side, 0 to 2 but anti-Stokes. So Stokes lines appear in the lower frequency region, anti-Stokes lines appear in the higher frequency region. Now listen carefully. Now, are these lines 0 to 2 line, 1 to 3 line, I'm sorry, this is 1 to 3, next 2 to 5, 2 to 4, 2 to 4 line, 3 to 5 line, okay, you will get so many lines. Now, if nuclei present in the molecule has spin, then it affects the intensity of these lines. Either there may be alternation in intensity, this line may be more intense, this line may be less intense. Again, this line may be more intense, this line may be less intense. So there may be alternation in intensity occur. See, let me show you here. What is meant by alternation in intensity? See, this is the Rayleigh line. First line may be less intense, second line may be more intense. Second, third line less intense, fourth line more intense. Less intense, more intense. Like that, the intensity alternates. So there is an alternation in intensity, right, appears when the nuclei of the molecule has spin. Sometimes this also may happen. Sometimes what will happen, see, I am just showing you only the Stokes line. Similar thing happen in the anti-Stokes. This is the Rayleigh line. Sometimes what will happen, some lines may be missing. For example, see, 0 to 2 line may be missing. 1 to 3 line will appear. Again, 2 to 4 line may be missing. Then you will get 3 to 5 line. Some lines may be missing, right? Yes, this is also due to the effect of the nuclear spin. So, because of the nuclear spin, right, nuclear spin effect, okay, rotational Raman spectrum, right, either exists or either appears as alternation in intensity, or it appears with some missing of lines, right? So, nuclear spin affects the rotational Raman spectrum. So, it causes either alternation in intensity of rotational lines, or sometimes some rotational lines may be missing, right, due to the effect of nuclear spin. Okay, now we'll try to understand, right, how the alternation in intensity occur, how missing of rotational lines takes place. Listen carefully. Homodiatomic molecules, right? See, depending upon the nuclear spin, right? Observe carefully. If nuclear spin is half integer, 1 by 2, 3 by 2, 5 by 2, etc., we call the nucleus as fermions. When in the case of homodiatomic molecule, the two nuclei are identical. So if one nucleus is fermion, the other nucleus is also fermion. When the molecule undergo rotation, exchange of two identical fermions takes place. In that case, total wave function must be anti-symmetric. I wrote simply AS, meaning anti-symmetric. Instead, if I takes values 0, 1, 2, 3, integer values like this, then the nucleus is called boson. In the case of homodiatomic molecule, both the nuclei are identical. If one is boson, the other one also boson. They are identical boson. When the molecule undergo rotation, what happens is that two identical bosons exchange their position. When two identical bosons exchange the position, then the total wave function must be symmetric. Okay, note down. So this is based on Pauli principle. Okay, this is based on Pauli principle. Then total wave function of the molecule, okay, is the product of translation, electronic, vibration, rotation, and nuclear spin. Okay, total wave function is the product of all these 5 wave functions. Observe carefully. When the molecule undergo rotation, right, translation wave function does not change. Does not change means it is always symmetric. Translation is always symmetric. Electronic is always symmetric. When the molecule undergo rotation, see, mostly molecule is present in the ground electronic state. When the molecule undergo rotation, the ground electronic state never gets disturbed. Therefore, it remains symmetric. Similarly, the vibrational state, that also remains symmetric. So remember, psi translation, psi electronic, psi vibrational, they are all always symmetric. So if this is symmetric, this is symmetric, this is symmetric, symmetric into symmetric is symmetric, symmetric into symmetric is symmetric. So this product is always symmetric. Therefore, you need not consider these three. Because if I multiply symmetric with these, I am going to get the same result. So I can write total wave function simply as rotational state wave function into nuclear spin wave function. Okay, good. So total wave function, right, is equal to, right, wave function of the rotational state into wave function of the nuclear spin state. Okay, listen, if exchange of two identical fermions takes place, I have told you, when two identical fermions exchange the position, total wave function should be antisymmetric. Okay, now we know very well total wave function is nothing but the product of these two alone. So here I have two possibilities. What are the two possibilities? Number one, see, if rotational state is symmetric, nuclear spin state must be antisymmetric, so that symmetric into antisymmetric is antisymmetric. We should get total wave function as antisymmetric, because for fermions I is equal to 1 by 2 or 3 by 2, 5 by 2, etc. When two identical fermions exchange their position, total wave function must be antisymmetric. For total wave function to be antisymmetric, there are two possibilities. What are they? Either this should be symmetric and this antisymmetric, or this should be antisymmetric and this should be symmetric. Okay, symmetric into antisymmetric is antisymmetric. Antisymmetric into symmetric is antisymmetric. Is this clear to all? Suppose if two identical bosons exchange their position, if one nucleus is boson, other nucleus is also boson, because we are talking about homodiatomic molecule. So when the molecule undergo rotation, two identical bosons exchange their position. According to Pauli principle, when two identical bosons exchange their position, then the total wave function must be symmetric. What is total wave function? Total wave function is nothing but the product of psi j and psi ns. Okay, so here also we get two possibilities. What are the two possibilities? Number one, if psi j is symmetric, psi nuclear spin must also be symmetric. Therefore, symmetric into symmetric is symmetric. So total wave function is symmetric. What is the other possibility? If psi j is antisymmetric, psi nuclear spin must also be antisymmetric. Antisymmetric into antisymmetric will also give total symmetric. Okay, so this product is symmetric, this product also symmetric, so total wave function is symmetric in the case of exchange of identical bosons, right? I have told you translational wave function remains symmetric, electronic wave function remains symmetric, vibrational wave function also remains symmetric during rotation, but the wave function psi j, rotational state, right, wave function of the rotational states, that depends on the electronic state of the molecule. Okay, so if electronic state is psi Gerard plus or psi sigma Gerard plus or sigma ungerard minus, Gerard plus is symmetric, ungerard minus also symmetric. Okay, if molecule is present in this electronic state or in this electronic state, okay, in both the cases, listen, the rotational states having even j values, j 0, 2, 4, 6, etc. are symmetric, and the rotational states with the j value 1, 3, 5, 7 odd numbers, okay, they are called as anti-symmetric states. Okay, symmetric, this is anti-symmetric. When if the electronic states are sigma Gerard plus or sigma 1 Gerard minus, for these electronic states, even j values are symmetric, odd j values are anti-symmetric. Similarly, if molecule belongs to sigma Gerard minus or sigma 1 Gerard plus, they are all term symbols, right? Electronic state term symbol for diatomic molecule. If molecule belongs to sigma gerade minus or sigma 1 gerade plus, in these electronic states, okay, J odd numbers, okay, 1, 3, 5, etc. These states are symmetric. Odd number states are symmetric. Even number states 0, 2, 4, 6, etc. are anti-symmetric. Okay. Yes. So I have told you about the rotational states of the molecule and which are the rotational states are symmetric, which are the symmetric states are, which are the rotational states are anti-symmetric. Okay. We discussed based on the electronic states. Now we'll discuss about the nuclear spin state. You know very well, in the case of diatomic molecule, homodiatomic molecule, okay, the two nuclei are identical and they also have the property of spin. If both the nuclei spins in the same direction, okay, then we call that state, okay, as ortho state. And the nuclear spin wave function is symmetric. It is called symmetric spin state. If the two nuclei spins in the opposite direction like this, it is called parastate. Okay. In parastate, the nuclear spin wave function is antisymmetric. Okay. So, in the case of homodiatomic molecule, right, the two nuclei may have same spin or may have opposite spin. Depending upon that, the molecule may be, the nuclear spin function of the molecule may be symmetric or antisymmetric. Okay. Listen, total number of nuclear spin states for a homodiatomic molecule. This is applicable for homodiatomic. Homodiatomic molecule. Okay. For homodiatomic molecule, total nuclear spin state is 2i plus 1 the whole square. 2i plus 1 is for one nucleus. 2i plus 1 for another nucleus. If you multiply, you will get 2i plus 1 whole square. This is total number of spin states. Out of these spin states, how many are symmetric and how many are antisymmetric? Number of ortho states, also called symmetric spin states, is equal to I plus 1 into 2i plus 1. If you use this formula, you will get how many symmetric spin states are available for the given molecule, homodiatomic molecule. Then number of parastates, also called antisymmetric spin states, is equal to I into 2i plus 1. This formula will give number of antisymmetric spin states. Okay. Okay, this is our first example, hydrogen molecule. You know very well, in hydrogen molecule, okay, we have two hydrogen atoms and each hydrogen atom has a nucleus with I is equal to half. Okay, so in hydrogen molecule, the two nuclei, right, have I is equal to half. Therefore, they are fermions. Okay, one nucleus is fermion, another nucleus also fermion because it is homodiatomic molecule. So, I is equal to half for one nucleus, I is equal to half for another nucleus. They are both are identical. They are identical fermions. When the molecule undergo rotation, what will happen? The two identical fermions are exchanging the position. Exchange of two identical fermions takes place when the molecule undergo rotation. Okay, so keep this point in mind, very important. When exchange of two identical fermions takes place, you know very well, total wave function must be antisymmetric. When two identical fermions exchange the position, total wave function must be antisymmetric according to Pauli principle. Right? And you also know that ground electronic state of hydrogen molecule, okay, yes, this is the term symbol, singlet sigma gerade plus. This is the ground electronic state of hydrogen molecule. Since it is sigma gerade plus, okay, J value 0 to 4 odd, even J values, right? Even J states are symmetric, odd J states are antisymmetric. In the case of hydrogen molecule, how many nuclear spin states are there? Total number of, this is total. Total number of nuclear spin states in H2 molecule. Since it is homodiatomic molecule, the formula is 2i plus 1 the whole square. 2 into I value is half. So in the place of I you put half plus 1 the whole square. Here 2 cancel. So 1 plus 1 is 2, 2 square is 4. So hydrogen molecule has totally 4 nuclear spin states. Now out of the 4, how many of them are symmetric spin states and how many of them are antisymmetric spin states? You can calculate this using this shortcut formula. Number of symmetric nuclear spin states is equal to I plus 1 into 2i plus 1. I value is half, so put I value half here and half here. If you put I half here, half plus 1 is 3 by 2. 2 into half is 1, 1 plus 1 is 2. So 3 by 2 into 2 will get 3. What is the meaning? Out of 4 nuclear spin states, 3 of them are symmetric nuclear spin states. And the remaining one is antisymmetric nuclear spin states. So 3 are symmetric and the 1 is antisymmetric.
Which page on?
In the case of hydrogen molecule, the 2 nuclei are fermions. When the molecule undergo rotation, 2 identical fermions exchanging their position. Okay. In that case, total wave function is antisymmetric. I wrote simply AS meaning antisymmetric as per Pauli principle. Okay. And here we have 2 possibilities. What are the 2 possibilities? To get antisymmetric, see the total wave function to be antisymmetric. For this, either rotational state should be symmetric and nuclear spin state antisymmetric, or rotational state antisymmetric and nuclear spin state should be symmetric. Symmetric into antisymmetric is antisymmetric. Antisymmetric into symmetric is also antisymmetric. So total wave function should be antisymmetric. So there are 2 possibilities. So remember, for symmetric rotational state, antisymmetric nuclear spin state will combine. And you know very well how many antisymmetric spin states are there? Only 1. How many symmetric spin states are there? Symmetric spin state 3. So listen carefully. You know very well in the case of rotational levels. Okay. See, what is the degeneracy of the rotational level? Degeneracy formula 2j plus 1. Without nuclear spin, without considering nuclear spin, if j is equal to 0, you put 0 here, 2j plus 1, I will get the answer as 1. So we have only one rotational state. If j equal to 1, if you put 1 here, you will get 3. You will get 3 rotational states. These are all rotational. One rotational state, 3, 5, 7, 9, like that it goes. As we go above and above and above, a number of rotational states increases. Degeneracy increases. Okay. Listen carefully. If this is so, listen, if transition takes place from 0 to 2, that line will appear with less intensity because I have only one state, population will be less. If transition takes place from 1 to 3, 1 to 3 transition will show little higher intensity because I have 3 states. 2 to 4 will give little higher intensity. So, from 0 to 2, to 1 to 3, to 2 to 4, the intensity supposed to increase. Supposed to increase, right? We should get a spectrum of this kind. Okay, 0 to 2, 1 to 3, 2 to 4, right? The intensity is supposed to increase like this. This is what normally we expect. But due to nuclear spin, right? The effect of nuclear spin, see here. Listen, J0, even J, no. Even J is symmetric. To symmetric, antisymmetric nuclear spin state will combine. Okay. How many antisymmetric nuclear spin states are there? Only 1. 1 into 1 will give only one state. Whereas if you come to J equal to 1, J equal to 1 is odd number, it is antisymmetric. Antisymmetric will combine with the symmetric spin state. How many symmetric spin states are there? 3. So 3 rotational state into 3 nuclear spin state. 3 into 3, you will get 9 states. Again, if you go to j equal to 2, j equal to 2 is even number. Even number means symmetric. Symmetric rotational state combined with the anti-symmetric nuclear spin state. Anti-symmetric nuclear spin state is only 1. 1 into 5 is 5. Whereas if you come to this, j equal 3 is odd number. Odd number rotational state is anti-symmetric. Okay. Anti-symmetric will combine with the symmetric nuclear spin state. Symmetric nuclear spin state we have 3. So 7 into 3 is 21. Yes, here we have 21 states. Now observe carefully. After the effect of nuclear spin, see the rotational levels. Listen, this level has only 1 state. This level has 9 states. Next level has lesser number of states. See. So if transition takes place from 0 to 2, I have only 1 state here. So this will appear with less intensity. Okay. If transition takes place from 1 to 3, in j equal to 1, I have 9 states. More number of states means more population. Okay. Therefore, 1 to 3 transition will appear with high intensity. If you go to, see I have similarly have j equal to 4 level here. J equal to 4 level, some numbers will be there. 2 to 4 transition, see carefully. 2 to 4 transition, here I have only 5 states. Okay. So 2 to 4 transitions involve only 5 states here in the ground level. So population is less, so intensity is less. Whereas 1 to 3 transition, here we have 9 states, so population is more, so intensity is more. So 0 to 2 transition will appear with less intensity. 1 to 3 transition will appear with high intensity. Again, 2 to 4 transition will appear with lesser intensity. Then 3 to 5 transition will appear with higher intensity. So we get alternation in intensity in the rotational Raman spectrum of hydrogen molecule. Is this clear to all? Right? This may not be the exact appearance of the spectrum, but it appears something like this. In the rotational Raman spectrum, we plot intensity versus scattered frequency. And this is the Rayleigh line. This is Rayleigh. First Stokes line corresponds to 0 to 2 transition, which appears with the lesser intensity. See, intensity is less. Whereas the next line will appear 1 to 3 will appear with high intensity. Why? Because j equal to 1 level has 9 states. 2 to 4 will appear with lesser intensity. 2 to 4. Why lesser intensity? Because j equal to 2 level has only 5 states. Then if you come to 3 to 5, 3 to 5 will appear with high intensity. See, less intense, more intense, less intense, more intense. So we get alternation in intensity in the rotational Raman spectrum of hydrogen molecule. Okay. Same thing happens in the anti-Stokes line. Okay, here also anti-Stokes line, right? First anti-Stokes line 0 to 2, second anti-Stokes line 1 to 3, third anti-Stokes line 2 to 4. Right? Here also you will get the alternation in intensity, right? 3 to 5, etc. Okay. Yes. This is how the spectrum will appear in the case of hydrogen molecule. Listen, all transition, all rotation lines are available. 0 to 2, 1 to 3, 2 to 4, 3 to 5. All rotation lines are available. There is no missing of lines. But there is an alternation in the intensity because of the nuclear spin effect. Okay. Yes. In the next class, we will discuss about deuterium molecule, okay, and the nitrogen molecule. Both will give the same idea, okay. But deuterium molecule, I value equal to 1, right? So first you start with the deuterium molecule and try to explain how the spectrum look like. Okay, yes. I'll leave it to you. In the next class, we will discuss this.